All right, today we're going to tackle a really cool and classic computer science puzzle. How do you find the exact point where two separate paths suddenly merge into one? It's a fantastic problem that has a surprisingly elegant solution. So, yeah, let's just dive right in.
So here's how we're going to break it down today. First, we'll get a handle on the Y-shaped puzzle itself. Then, we'll uncover what I call the Head Start secret. This is the key idea that cracks the whole thing wide open. From there, we'll see the algorithm in action, turn that logic into some actual code, and finally, we'll check out just how efficient this whole approach really is. Okay, first up, the Y-shaped puzzle. This is all about finding that precise moment where two completely different journeys become one and the same. To really wrap your head around this, just picture it like this. You've got two teams, and they're on totally separate scavenger hunts. They start in different places, they follow their own unique clues, but at some point, their paths cross and merge. From that point forward, they are following the exact same trail of clues to the finish line. So the big question is, how in the world do you find that very first clue they both share?
Now, in our world, in the computer science world, these scavenger hunt paths are what we call a linked list. And honestly, the best way to picture a linked list is just to think of a train, right? Each car in the train is a node. It holds a piece of information. And each car is coupled to the next one. It points to the next car in the line. It's a super simple but really powerful way to chain data together.
Okay, so that brings us to the actual challenge. We're given two of these linked lists, two of these data trains. We know for a fact that somewhere down the line, they merge. They start sharing the exact same nodes all the way to the end, forming this perfect Y shape. Our mission, should we choose to accept it, is to find that first common node, the intersection point. And here's the kicker. We have to do it efficiently. So, how do we actually solve this thing efficiently? Well, the answer lies in a really clever trick, what I like to call the head start secret. This is the core idea that makes the whole solution so brilliant. Think about it like a race. You've got two runners, one at the start of each path. They start at the exact same time, run at the same speed. But if one path is longer than the other, they're obviously not going to get to the intersection at the same time, right? The runner on the shorter path is going to get there first and just have to wait around. And this, right here, this is the aha moment. What if we could figure out exactly how much longer one path is than the other? And then, what if we gave the runner on that longer path a head start equal to that difference? If we do that, well, suddenly, both runners are the exact same distance from the intersection. Now, if they start running and take one step at a time together, they are absolutely guaranteed to meet right at the merge point. Okay, with that core idea locked in, let's see how this actually builds into a repeatable process. It's time to turn this clever little idea into a concrete set of steps. You know, it really just boils down to a super simple four-step method. First thing you do, run through each list just to count how many nodes it has. We'll call those lengths L1 and L2. Step 2, find the difference between them. That's our D, our head start distance. Step 3, take the pointer for whichever list is the longer one and just bump it forward D times. And just like that, the starting lines are even. And now for the fun part, step 4. You just move both pointers forward one node at a time, perfectly in sync. The very first time those pointers land on the exact same node, bam, that's it. That's your interception. That logic is just so clean, isn't it? But what does it look like when you actually have to write it? Next up, let's see how this all translates into a real C program. And you really don't have to be a coding wizard to see how the program just mirrors those 4 steps we talked about. You'd probably have a little helper function, something like getCount, to do the counting for you. Then your main function, let's call it getIntersectionNode, would find the length difference, use a simple for loop to give the longer list its head start, and then finally use a while loop to march them both forward until they meet. And this little snippet of code right here, this is the engine of the whole solution. It's so simple, but it's where the magic happens. It basically just says, hey, as long as our 2 pointers aren't the same, just move each one forward to the next node. This loop only stops when they finally land on the same spot, which, thanks to our clever head start, we know for sure is going to be the intersection. It's basically the code version of our 2 runners finally high-fiving. So we've got an algorithm that works, and we know how to code it up. But the real question any good programmer asks is, how well does it work? Let's actually measure its efficiency and see why this algorithm isn't just correct, it's also really smart. You know, to really appreciate how good this solution is, let's compare it to the brute force way of doing it. You could take the first node of list A and check it against every single node in list B. Then take the second node of A and do it all over again. I mean, it would work eventually, but oh my gosh, would it be painfully slow if your lists were long. Our Head Start method, on the other hand, is just so much faster because we only have to walk through the lists a couple of times.
Now, we can measure this formally with something called big O notation. The time complexity is O of m plus n. All that means is that the time it takes to run is directly tied to the total number of nodes in both lists. If the lists get twice as long, it takes about twice as long to run. It scales beautifully. But what's maybe even more impressive is the space complexity, O of 1. This means our algorithm uses a constant, tiny amount of extra memory. It doesn't matter if our lists have 10 nodes or 10 million.
So let's just boil it all down. We've solved this puzzle in a way that is incredibly efficient with both our time and our computer's memory. We didn't have to make any extra copies or use fancy data structures. The whole thing is fast, it's predictable, and it's lean. In the world of algorithms, that is an absolute win. When you think about it, the real secret here was about leveling the playing field, right? It was about giving one side a head start to make the rest of the problem almost trivial. So the question I'll leave you with is this. What other problems, maybe in coding, maybe even in life, seem really complex on the surface, but could be made way simpler if you just found the right way to line up the starting points?